Welcome to Berkey Academy's Financial Math Formulas Video 2, where in this video we're going to be talking about annuities and perpetuities. An annuity is any time you're either paying or receiving a stream of equal payments over a certain period of time. So a stream of payments for n years, or it could be in months or days, really, but usually months or years are the most common cases. What we'll be doing with annuities is we'll be coming up with formulas for the present value of an annuity. That is, if somebody's going to be paying me a certain amount of money for, say, 10 years in the future, $100 at the end of each year for 10 years in a row, how much is that worth to me now? We'll also answer the question, what if somebody's going to be, say, paying me $100 a year for n years? How much money would that be worth in the future at the end of those 10 years? And we're normally assuming that I'm going to be reinvesting those payments. So if you give me $100 at the end of the first year, and I put that in the bank, and then $100 the second year, and I put that in the bank, and it's always earning the same amount of interest, how much would I have at the end of those 10 years? We'll also talk about a perpetuity. A perpetuity is the same exact idea, except at least theoretically, you're going to be getting those payments forever. Now, with a perpetuity, we're going to be calculating present values only, because if you add up how much money you're gonna have from a perpetuity at the end of time, well, we're adding up an infinite amount of money. And so we know that calculation would be infinity, except we'd be doing that calculation an infinite amount of time in the future. So it's kind of a confusing thing to think about. So basically what we'll be calculating here is if somebody promised to pay me $100 or $1,000 at the end of each year, from now until the end of time, how much should I value that today if I know some interest rate that I can think of that would be appropriate for that? Now, just to review real quickly what we did last time, here are some of our formulas. We calculated simple interest, which is just how much money you're starting with, times 1 plus the interest rate. Compound interest, when we're doing this, but we're leaving the money in so that we can earn interest on the interest, is present value times 1 plus r to the n. How many years will it be? However, this formula generalizes to where it's not just for yearly compounding. Quite often you'll see cases where monthly or daily compounding is relevant. And so then we have this formula where basically we take that interest rate R, which is an annual percentage rate, divide it by how many times are we compounding per year. So K would be either 12 for 12 months, 365 for 365 days. And so we're coming up with a monthly or a daily interest rate. And then we're raising that to the number of periods, the number of days or the number of months that it should be compounded in times K. Now, in general, anything that you can do with compound interest or compounding K times per year, quite often we'll just write a simpler version of the formula, say this standard compound interest formula, but that doesn't mean that in more complicated situations we couldn't do the same kind of formula as we would if we were looking at this compounding multiple times per year formula. Okay, so what I'm going to do today when we're talking about annuities and perpetuities, I'm going to just use the simpler version of the formula, assuming we're compounding once per year. But it's very easy to substitute in, say, a monthly interest rate, and then we're going to raise it to the appropriate power. How many times are we going to be compounding? In the last video, we also looked at continuous compounding, which is theoretically in the limit. If we compounded not monthly or not daily and not every minute, but every instant, in the limit, we have this formula where the future value is the present value times e, the base of the natural logarithm, which is approximately 2.71828, raised to the annual interest rate times time. We're not going to be using this formula anymore in this video today, but we will be looking at present values quite often. And present values is just simply if you take one of these future value formulas and you solve it for present value, we just divide both sides by this 1 plus r or 1 plus r to the n or whatever, and we end up with the present value is taking the future value and dividing it by 1 plus r to the n, or again, we could use multiple compounding by making an easy substitution here, right? And we also covered the rule of 72, which is a quick rule of thumb. See that video if you want to learn more. Let's start diving into annuities and perpetuities. So let's start off by looking at perpetuities, and then we'll look at annuities. Suppose somebody promised to pay me $100 each December 31st forever, and today is the beginning of the year, January 1st. This is just the standard way that these formulas are defined. So the time period we're thinking of starts at the beginning of the year, but our first payment won't begin until the end of the year. So if they're going to pay me $100 on every December 31st from now till the end of time, what's the value to me now? In other words, what's the most I should loan someone if they made me such a promise that I could believe? And the interest rate was 7%. Now, let me just write down the formula, and then I'm going to show you the derivation of this formula, and then we'll use the formula, okay? So let me just write the formula here real quickly. So the present value of a perpetuity, it's a very simple formula. Present value equals how much is this payment that they're going to be paying me? So we'll call that PMT. And let's divide that by the interest rate, written as always, as almost always, except for in the rule of 72, written as a decimal. So we'll call that R. So in this problem, to get the answer, what we would just do, I'll just go ahead and do that, would be the $100 they promised to pay me every year, starting at the end of this year, divided by the interest rate, which we said was 7%. So it'd be $100 divided by 0.07. And what we get is about $1,428.57. So that's how much that infinite stream of payments should be worth to us now. So just to help everybody get a visual understanding of what's going on here, when we're adding up this infinite stream of payments, the present value of those payments that are farther in the future here get close to zero pretty quickly. So after about 80 years, the present value is basically nothing. And we can look at what happens as we add up more and more and more of those payments in the future. We're getting closer and closer and closer to that present value amount, a little more than $1,400 that we calculated. And over here in the columns, you can see that those payments 80 years from now, 100 years from now, are worth only, 10 cents to 25 cents or so. And they're getting smaller and smaller, of course. And of course, this Excel spreadsheet has a link for download in the video description. The whole idea here is that if we did the reverse, if somebody gave us $1,428.57 and we invested that in a bank account that was going to pay us 7% interest times 0.07, then what we'll get out of that is $100 in interest every year from now till the end of time, right? So it really is the value. It's the same thing. So somebody should be relatively indifferent between having $1,428.57 today or this promise, as long as they know the promise is good, all right? So in this video, I'm always going to show you two different ways that you can derive these formulas. One, the smart way. If you really understand what we're doing, you can do it a much easier way. Or I'll also show you the standard way, which I think is much less intuitive and involves some mathematical tricks. If you understand what I just said, that really what the present value is answering the question, how much money do we need if we were to invest it at 7% interest to earn this stream of $100 from here throughout eternity? Then here's putting that calculation into words. We want the payment to be $100. So we could write the formula this way. Payment is going to be $100. And we want that to be equal to how much money we have to have in the bank, the present value today, times the interest rate, so that the amount of interest we earn every single year is going to be $100, right? The interest is $100. The present value, we don't know. But we know that we can invest this present value in the bank at 7% interest, so 0.07. And really all we're doing is we're solving this simple equation for present value. So of course the formula for a perpetuity is going to be present value equals payment over R. That's really all we're doing when we solve this for present value, right? Payment divided by R. Now let me go ahead and show you the official derivation that a lot of your professors in classes might want you to be able to replicate. So instead of writing it all out in my terrible handwriting, I went ahead and typed it all out here, and we'll go through it very quickly together. What is a perpetuity? Well, the present value should be equal to that payment I'll get 1 year from now divided by 1 plus the interest rate, plus the present value of the second payment, which would be in 2 years' time, divided by 1 plus the interest rate squared, right? This is just multiple uses of that present value formula, plus the payment at the end of the third year divided by 1 plus R cubed, etc., 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 going on to infinity. Now, to simplify this, a lot of these formulas you have to do a little trick to cancel out an infinite number of these terms. And here's the trick you use for this formula. You multiply both sides by 1 over 1 plus R. If we multiply that side by 1 over 1 plus R, and then we multiply everything on the right side here similarly, then what we'll end up with is something that looks like the formula here in number 2. So of course on the left, present value over 1 plus R equals, so all these denominators on the right hand side are going to be increased in power by 1. So this term goes away basically, and then we're still going to have all the exact same terms going out to infinity over here. So there's only really one difference on the right hand side here, and it's that missing term in purple there. So now the trick says to subtract equation 2 from equation 1. So what we're going to have is the present value from the first equation minus PV over 1 plus R from the second equation equals, and again, all this stuff cancels here over on the right, except payment over 1 plus R. So that stays here. So now what we want to do is just take this equation and solve it for present value. But present value here occurs twice. And so for me, the easiest way to see that is to multiply the entire equation by 1 plus R. And so then we're going to be canceling, and then we have the 1 plus R here times PV. So that's what's in this line. And then I expand this term. PV times 1 is PV. PV times R is RPV. And so we have 3 terms here with PV involved. But here we have a PV and a minus PV, so those cancel, so that just leaves us with R times PV equals the payment. Divide both sides by R, and we're done. And this is our formula for the present value of a perpetuity. Not that difficult, just involves a little trick. So it turns out that this little formula for perpetuity is a really important one to know, and it in itself can help us with a shortcut to figuring out some more complicated formulas. And I'm going to show you that at the end of the video. So just take the payment that you'll be receiving and divide it by the interest rate. If this was a payment you are going to be getting every month from now till the end of time, the only thing you'd need to adjust is divide this yearly interest rate, 7%, by how many months there are. So we divide it by 0.07 divided by 12 if somebody was paying us $100 every month. And of course, that's going to be a bigger value because we're getting $100 every month, not just once a year. So the real world application of perpetuities is probably most realistic if you're thinking about an investment in something like land. And you assume that this land is going to earn you money. Maybe this land is growing corn, or maybe this land is being used to add value to your sheep or your cattle as you graze animals on this land. So if you own some kind of asset, a real asset like land or a forest or a farm, where every year that farm or that forest is going to be returning you a certain amount of money into the future, a way to think about what is the value of this land is to use this perpetuity formula. How much money are you getting from this land every year? And what is the interest rate that you could earn in a bank if you, instead of having the land, had the money, had the value of the land? Then what we want is the value of the land to be equal to the amount of money you'd need to deposit in the bank that would provide an equivalent stream of income. Another sort of real-world example of a perpetuity is what we call a consol, C-O-N-S-O-L. And several governments, the British government and the United States government, have issued consols. It's a special kind of bond where, in theory, you buy this bond, and in this case, this is a $100 bond. And this was issued in around 1877. And so if you bought this bond for $100, then what you would get in return is a stream of payments. The stream of payments that this particular consol would give you would be $4 a year, but the way they actually paid this interest was $1 per quarter. So $1 every 3 months. So if you wanted to see, is this a good investment? Should I buy this console for $100? What you would want to do is look at your other opportunities you would have for using that $100 to make money. If you could invest that $100 in a way where you're going to be making more than $1 per quarter, then that other investment would be better than this. Now, if we were to use the perpetuity formula to calculate this, what we would need to know is the annual interest rate. And let's suppose that the annual interest rate at this time was 8%. And let's suppose that there was a bank in town that was willing to pay you 8% a year, but pay you every quarter, compounding your interest every quarter. Then what we would do is take our interest rate, 8%, and we would divide it by K, and K here would be 4 times per year, 4 quarters per year, and we would get that our effective interest rate each period, each quarter, is going to be 2%. And so our payment would be $1. The relevant interest rate here is not going to be the 8%, it would be 2% per quarter. And so our present value, how much this console special kind of bond would be worth to us, is the payment, $1 every quarter, divided by our alternative interest rate we could get at a bank in town, 2% per quarter. And the present value of this console to us would be only $50. It's not worth paying $100 for this bond, which, if you think about it, if it's only paying $4 per year, but it's costing you $100, really it's paying 4% interest per year, right? But if you have an alternative investment where you could earn 8% interest, you're not willing to pay $100 for this console. Most often, bonds don't sell for their face value. This console has a $100 face value, but most of the time, you're not actually going to be paying that face value because the real value is based on what other alternative interest rates there are for similar assets. Now, in fact, these consoles weren't true perpetuities. The fine print down here actually says that this bond is going to pay $4 per year, paid quarterly, or $1 per quarter in perpetuity into the future until at least 1907. So that's where this 1907, 30 years. So it said, we're going to pay you this stream of payments every quarter for at least 30 years. However, at any time after 1907, the United States government can decide that they're going to call in the bond. And if they call in the bond, what that means is they're going to pay off this $100 face value here, and in return, they're going to cancel that stream of payments. So really, if we're going to analyze a console like this that can be called after 30 years, it's not really an infinite stream of payments for $1. It's more something we would want to analyze in 2 parts. There's this stream of payments for 30 years we know of, and then maybe we'll get our $100 back in 30 years, and maybe we won't. The way it's worded here is, so it is redeemable at the pleasure of the United States government anytime after that 1907 date. how could we calculate the present value of a perpetuity that starts in the future sometime? Well, we already know how to find present values. We're just going to use that basic present value formula, and we're going to assume some compounding here as usual. So our basic present value formula for something that occurs in the future is to take the future value, divide it by 1 plus r to the n power. So one way to think about this is, well, if I got a perpetuity, a promise starting today that you will start paying me at the end of this year, well, that would be worth $1,428.57. If this promise doesn't really start happening until 10 years from now, then we're going to need to adjust that by dividing it by 1 plus r to the n. I know that's slightly complicated, but I also want you to think about how simple this is. So all you need to do to any sort of value, if it's not really a value that's appropriate for today, if it's something that's going to happen in the future, you just take the present value of that thing. It's like we're not receiving $1,428.57 until 10 years from now. One way to think about this is just to take the $1,428.57 and then divide that by 1 plus r to the n. Or in this case, if we're assuming that the interest rate is still 0.07, 1.07, and here n is 10 years. One of the trickiest things to me about these formulas is trying to remember when is it that these payments are supposed to actually start, right? So the perpetuity formula assumes the first payment won't begin until one period from today. It could be 1 year, could be 1 month, depending on the context. So if the first payment's going to be 11 years from now, then perpetuity itself, that present value, is 10 years from now. So let's go ahead and calculate this value, though. So the value we get for this particular problem is $726.21 approximately. I'm just rounding things to the nearest penny here. Sometimes we want to think about this formula. So here's the present value of a perpetuity that doesn't start until n years in the future would be payment divided by r. That's the present value of the perpetuity. But the perpetuity doesn't really start for n years in the future, then we'd want to divide that by 1 plus r to the n. We're going to see this formula a little later on. When we derive the next formula, this future value of an annuity, we're going to derive it a different way than the standard way, and you're going to see that we get the same thing. And if you can follow that, you can follow anything that I could possibly talk about in this series. Okay, well, let's go on to the future value of an annuity. So as I said, we have to be real careful about when we specify these payments are going to start. Sometimes you'll run into cases where people do things a different way than is standard. For example, and a good example of an annuity is house payments. Making a house payment is every month you pay money to the bank and eventually you pay off everything you owe and you own your house. The standard way is you don't start those payments for your mortgage payment until the end of the month after you sign the contract. There are some banks out there, however, that require the payment the first payment, the day you sign the contract. And it's a different value to the bank. The bank is getting all those payments earlier, 1 month earlier than before. And you're like, well, that doesn't matter much. It actually does. Let's talk about a non-standard case. Number 3, suppose today is January 1st, 2021, and let's calculate the future value of an annuity, but this is not the standard case. The standard case we'll do in a second. Suppose we're going to make 3 deposits of $100 at 7% interest, beginning today. What will the value be in the future on January 1st, 2024? So what we're going to do here is just do each of these payments separately. There's going to be 3 payments, 3 deposits of $100. They begin today, and then we get another payment on January 1st, 2022, and January 1st, 2023. How much money is this going to be that we have on January 1st, 2024, assuming we're depositing all this money in a bank account earning 7% interest? Let's just do this separately. for right now. So let's take the first payment. We get one payment today, so that's worth $100 today, of course. And if we put that in the bank today and we leave it in the bank for 3 years, we're going to have 100 times 1.07 to the third. And then next year, we're going to get another $100. And we're going to put that in the bank. And we're going to let it sit in the bank for 2 years, right? From January 1st, 2022 to January 1st, 2024. So we're going to have another $100 plus, we're going to take that $100, multiply it by the first term to take this other amount into account. We're going to also want to multiply that times 1.07 squared. So we have 100 times 1.07 cubed, that's the first payment, plus 100 times 1.07 squared, that's the second payment, plus the third payment is going to be 100 times 1.07, but that's just to the first power because it's just going to be in the bank from 2023 to 2024. So there's one way we could write this formula. We could calculate them all separately. I've just collected these three terms together to make it slightly easier to write down. So let's add up all these values. What is 1.07 cubed plus 1.07 squared plus 1.07? Well, when I add all those things up, I'm getting approximately, it's going to be $100 times about 3.439943. Now, one reason why you might want to do this separately is now we have a number, a constant, that we can multiply times any payment that they're going to be making to us. Once we have that 3.439943, we just multiply it times the 100, and that's easy. We can do that in our heads. We're going to end up with about $343.99, right? Plus about a half a cent here if we just kept going on. Let's do number 4. This is the standard kind of assumption. If you see a textbook problem asking you about an annuity, normally they're going to be assuming that today is, say, January 1st of a given year, and then what's going to happen is somebody's going to give us $100 at the end of this year, kind of like the perpetuity, right? And then they're going to give us another $100 the year after that on December 31st, and the year after that on December 31st. So what is the value? How much money would we have if we were depositing and investing this money at 7% interest in the end? Well, we can see it's going to be a very similar thing to what we did up here with one adjustment, right? What we're really going to be wanting to do is take these same terms that we had from the previous problem, but we're going to want to reduce the exponents by 1 for each of these three cases, right? So instead of 1.07 cubed, we're going to have squared. Instead of squared, we'll have to the first power. And here, instead of to the first power, we'll have to the 0 power. And remember, anything to the 0 power just equals 1. So just to rewrite this, we'll have 100 times 1.07 squared plus 1.07 plus 1. And if we add up all those numbers in our calculator, we're going to get a smaller constant than this 3.439943 because we're not going to have as long for this money to be reinvested in the bank. So it turns out this is going to be 100 times 3.2149 approximately. So the future value of these promises in the future, if they actually give us the money and we reinvest it as we get it, would only be $321.49. So it's a slight change in the timing of the payments, but it does make a decent size difference in how much money you'll have after you get this money and you invest it. Now, what we've just done here is not that difficult because we're only talking about a stream of 3 payments, right? Normally, we're talking about a stream of many more payments than this. If we're talking about payments on a mortgage, a 30-year mortgage, paying once every month, is going to be 360 payments. We don't want to have to do all these little terms individually and add up 360 of them, right? It's going to be a real pain even if we had to do this for 10. So we need a formula that will handle this for us. The formula that handles this for us, we usually call the FVIFA stands for the future value interest factor of an annuity. And this FVIFA, future value interest factor of an annuity, is basically just looking at these terms here. What is the sum of all those interest terms that we will then multiply times the payment that we're interested in, okay? Let's go back to our formula derivation sheet and let's derive this FVIFA formula. So here's the standard method, and again, at the end of this video, I'm going to derive it a different way that makes a whole heck of a lot more sense, I think. Not that this is too bad. So since these payments start 1 year from now, the money we get first is going to be in the bank for n-1 years, right? And then the money we get at the end of the second year will be in the bank for n-2 years, earning interest. So how much money will we have in the future at the end of this stream of payments? And then the last term is always going to be raised to the 0 power because we're getting that payment on the last day, and it's the same day we're calculating the future value. So somebody hands us the payment and it doesn't have any chance to earn interest, so this just becomes 1. Let's let x be 1 plus r. Simplifies writing it down and thinking about the math that we're doing here. Everywhere we see 1 plus r, we're just going to write x. And that gives us something like an equation 1 here. The trick is to take that same formula and multiply both sides by x. So on the left we have x times whatever this interest factor is that we're trying to derive. And so x to the n-1 becomes x to the n. X to the n-2 becomes x to the n-1, etc. And the x to the 0 becomes x to the first power. So these two on the right side are the same, except for the x to the 0 in the first equation and the x to the n in the second equation. Now we use a similar trick to what we saw when we were deriving the formula for a perpetuity. We take equation 1 and we subtract equation 2 from it. So on the left-hand side, we're going to have FVIFA minus x times FVIFA. And then on the right-hand side, we're going to have x to the 0 power minus x to the n. Because all of these other terms are going to be subtracted away. And then we just need to solve for what we're really trying to find, which is the future value interest factor of the annuity. And so we can collect the FVIFA times 1 minus x. That's the same thing here and here. We know that x to the 0 power is just 1, so we're just making that substitution. Minus x to the n, that's the same thing. And then we divide both sides by 1 minus x, and there we go. And finally, we're going to need to resubstitute. Everywhere we see an x, we're going to need to put the 1 plus r. So let's see what happens when we do that. So we have 1 minus 1 plus r to the n divided by 1 minus x, and 1 minus x is 1 minus 1 plus r. If we distribute that through, we're going to end up with 1 minus r. And of course 1 minus 1, those are going to cancel, and we have minus r. Most of the time when you see this formula written, they'll write it as 1 plus r to the n minus 1 over r. And here we're just bringing that minus sign up top, so this becomes minus 1, this becomes plus 1 plus r to the n, okay? Just reversing those two terms. So here's our future value interest factor of an annuity formula, and what it gives you when you plug in the numbers for our example here. So plug in n equals 3 and plug in r equals 0.07. It gives us this 3.2149 that we multiply times however large the payment is to get that future value we'll have after receiving all those payments. Now sometimes when there's an annuity, we also want to know the present value. How much is this promise of the stream of future payments worth today? One way to get that is just to take these two future values that we calculated, the $343.99 and the $321.49. Again, the difference being that This one, the first payment we get now. And this one, in the more standard case, we assume that the payments don't actually start for one period in the future. If we want the present value, just use our standard present value formula, divide those amounts by 1.07 to the third power, because those future values are calculated 3 years from today. And so what we get is $280.80 if the payments start now, and $262.43 if we have to wait for a year to get that first payment. Let me go to Excel real quickly so that we can imagine what these payments mean. Again, we always want to think about present values as being the amount of money I would need today to be able to replicate the stream of payments we're talking about. So in the first case, when the payments begin today, we start off with a present value of $280.80. If we had that much money, we could withdraw $100 today because we're getting that first payment now, and we'd have $180.80 left. We leave that in the bank earning 7% interest so that on January 1st next year we'll have $193.46. We take $100 out, we have $93.46 left. We leave that in the bank earning 7% interest, and a year later we'll have $100, which we can take out, leaving us with nothing. It's the same payments as the annuity we were talking about. Now again, the standard case assumes that we don't take any money out right now. We wait until a year from now. So we don't need as much money because this original amount, $262.43, will earn 7% interest, and then a year from now we'll have that $280.80. Aha, right? It's the same number, but it's how much we would have a year from now since we're not starting the stream of payments until then. So we pull out 100 and we see exactly the same progression of values that we had here, except it's starting a year in the future. Now, just like this future value interest factor of an annuity formula that we derived, there's also a present value interest factor of an annuity formula. So to get this, we'll take the payments and multiply it by some number. We just take the future value of an annuity formula and then we divide it by 1 plus r to the n to get the present value of this number today. And then we just have to simplify that. So to simplify that, when we divide a fraction on the top by something on the bottom, we can just take that and put it in the denominator of the fraction that we were starting with. And actually, to simplify this, again, if we can do that, we can do this. We can move the r down. And the reason I'm doing this is to make it a little clearer how this simplification is going to work. If we take this numerator fraction here and split it into two parts, we're going to have 1 plus r to the n over 1 plus r to the n. Of course, that will cancel, right? And then we have this minus 1 over 1 plus r to the n. So this part is 1. And then we can rewrite this 1 over 1 plus r to the n as 1 plus r to the minus n. So minus 1 plus r to the minus n, all divided by r. And this is the most common way that I'll see that present value interest factor of an annuity formula written. And again, this formula is for that standard case when the payments don't start until 1 year from when we're calculating the present value. So what we would get if we plugged in n equals 3 and r equals 0.07 into this formula is $262.43. Actually, we'll get the 2.6243, and then you multiply that times how large the payment is, and then that would give us our $262.43 since the payments are $100 each. Now let's spend a couple of minutes just reviewing what we've done, and let's derive those formulas a slightly different way, a way that makes a lot more sense to me. And this is going to be important for what we do in the next video when we're calculating bond prices and mortgages, kind of the capstone here. Instead of memorizing formulas, I really like to know where the formulas come from, and this is going to get us there. So let's think about a 30-year annuity, and this is where we really need these formulas. 2 or 3 years, we can just do it by hand. With many years, we need these formulas. And to calculate the present value, let's think about it as the difference of two perpetuities. So a 30-year annuity is, starting now, we're getting a stream of payments, kind of like a perpetuity, right? Here's today, call that time 0. We're going to be getting these payments. So let's suppose it's a $1,000 payment that we're going to be getting every year. So we get these payments all the way out to 30 years from now, and we could pretend like it's a perpetuity. Except at this point, till the end of time, we don't get the perpetuity. We lose that perpetuity at this point. So this is a little weird to think about, but let's go through it one more time just to make sure you get it. An annuity is like a perpetuity starting today, but then in the future, when the annuity runs out, I'm losing a perpetuity then. It's like somebody's taken that perpetuity away from me in 30 years' time. So we get a stream of payment. It's just like it's a perpetuity, and we can pretend it's a perpetuity, but we have to account for the fact that in 30 years, someone's going to rob us of that perpetuity. So we have to subtract that off. So if we want to calculate the present value of an annuity, we can say that it's the value of a perpetuity, and we know that formula is just the payment divided by R. But then in 30 years from now, we have to subtract off the fact that that perpetuity disappears. So what's the value of that perpetuity in the future? It's the payment divided by R divided by 1 plus R to the n. So if you want to derive the present value interest factor of an annuity formula, this is just as valid a way to do it as using that kind of mathematical trick and subtracting two streams from each other sort of thing, right? So let's use this and just make sure we're going to get the same answer. So present value of an annuity for $1,000 for 30 years is going to be $1,000 as our payment, divided by R. Well, I said let's assume the interest rate is 5% here, 0.05. But then we have to subtract off the same thing because we're losing it in 30 years. So 1.05 to the 30. So what are we going to get here? Well, we're going to get this first term. If it was a perpetuity, it would be worth $20,000. But then we're losing the perpetuity 30 years in the future, so we're losing that $20,000 valued thing, but we're losing it in the future, so the present value of that is only 20,000 divided by 1.05 to the 30. Now 1.05 raised to the 30 power is 4.322. If we do those calculations, what we end up with is about $15,372.45. So it's worth less than if it was a true perpetuity, and this second term tells us how much less it should be worth. So if I'm ever sitting by myself and for some reason I need this present value interest factor of an annuity formula, and I just can't remember it, I can always sit down and in a minute I can rederive it by just manipulating this formula, because this makes perfect sense to me. And if we want to simplify this to make sure we're going to get the same thing, let me just run through that really quickly. So here we have our payment, however much that is, times this first term is just going to be 1 over R, and then this is going to be 1 over R to the n in the denominator, which we can write with a negative exponent. So 1 plus R to the minus n over R. And now you see how easy it is to derive this present value interest factor of an annuity formula if you really understand where it comes from. The payment times the present value interest factor of an annuity formula, which is just going to be 1 minus 1 plus R to the minus n over R. Just collecting those two numerators together in the top. So what if we need the future value interest factor of an annuity? We take the present value and we kind of do the opposite of what we just did a minute ago. Instead of dividing it by 1 plus R to the n, we're going to multiply by 1 plus R to the n to get that future value, 1 plus R to the n, and simplify. And of course, if we're careful, we'll get exactly the same thing. So that's going to wrap up this video where we learned about annuities and perpetuities, and we used these basic ideas to derive the formulas for the present value of a perpetuity. The future value of a perpetuity doesn't make sense to calculate because it will be infinity. We used some mathematical tricks to derive the future value interest factor of an annuity formula. Then we used our knowledge of present value to calculate the present value interest factor of an annuity. And then we went back and kind of did it using what I think is common sense. If you really understand the idea of annuities and present values and future values, you can just construct this present value of an annuity formula pretty easily just by setting it up. Use some care to simplify. You get that present value interest factor of an annuity formula. And if you want the future value, use the future value formula. Multiply it by 1 plus r to the n. So please join me next time for the final video in this Introduction to Financial Mathematics series, where we're going to talk about bond pricing formulas and formulas for calculating how much your mortgage payment should be. And it's going to build on exactly the same little blocks that we've been using. So thank you very much for joining me. I hope you join me for the next installment. And as always, if you have any comments or questions, please leave them in the comment section below.